Hello, my name is Ryan and I'm going to be going over this challenging problem. This problem says a photon of wavelength 250 nanometers ejects an electron from a metal. The ejected electron has a de Broglie wavelength of 0.85 nanometers. So this is similar to, this is kind of like the photoelectric effect. So basically there's this photon with a 250 nanometer wavelength, and it's ejecting this electron. So you can think there's like an electron down here. It has to go up a little bit to defeat the work function, and then it goes up even more to essentially get past, to have its now kinetic energy. So it now has this kinetic energy here. So the first part, is it asks us to calculate the kinetic energy of the electron. So the first thing I thought here was, could I use the formula? I was thinking I could use the formula lambda is equal to C over F. And I was like, hey, I could basically just convert our de Broglie wavelength here to our frequency and then just plug that into E equals HF. But I found out this actually doesn't work because this equation only works for photons, really, particles that are traveling at the speed of light, and the electron isn't going to travel at the speed of light. So I have to approach this from a different way. Basically, I know kinetic energy is equal to 1/2 mv squared, and momentum is equal to mass times velocity. So I combine these equations. I basically said P over the mass is equal to V. And then if you plug this back into this equation, I'll just scroll down so I can do that, we get kinetic energy is equal to 1/2 m times P over m squared. Then if we simplify this, we will get the kinetic energy is equal to 1/2 m times P squared over m squared. You'll see that this m and that m will cancel out, and we'll be left with kinetic energy is equal to P squared over 2m. So from here, all we need to do is find the momentum. What is P equal to? And then we can, to find that, we can look at our equation sheet, and we see that the lambda is equal to h over p. H is Planck's constant, which is 6.626 times 10 to the negative 34th, and we know this value here. They said at the beginning of the prompt that this value is the 0.85 nanometers. So we can plug that in. We'll convert this to meters to make our equations easier. So this is right now in nanometers, and we know there's 1 times 10 to the 9th nanometers in 1 meter. So we can convert that, and we'll basically get 0.85 times 10 to the negative 9th. And now we have h here, which would be 6.626 times 10 to the negative 34th. And we can just rearrange our equation to say P is equal to h over lambda. And then we can plug this value in. So then we can just do all the calculations at once. We can plug this back into our kinetic energy equation for h over lambda squared. You can see we're using this equation right there. We're plugging it back into that. And then we're multiplying 2 times the mass. So that means we just have to get P. P is equal to 6.626 times 10 to the negative 34th over lambda, which we found is 0.85 times 10 to the negative 9th. We found that to be meters. So we can plug that in. We know the mass of an electron. We can look at our equation. The mass of an electron is actually equal to 9.11 times 10 to the negative 31 kilograms. So we can plug that all into our calculator at once, and we can do 6.626 times 10 to the negative 34. Then we divide this by our lambda, which is 0.85 times 10 to the negative 9 meters. And then we square that value, because that is the value for this. So we square that value, and then we divide it by the mass of an electron, and we multiply that by 2. So we do divided by 2 times our mass of the electron, which is 9.11, times 10 to the negative 31. We plug that all in, and I get a value that says the kinetic energy is approximately equal to 3.335 joules, because energy is in joules. So that's the first part of our problem. Now our second part, so we got A, we're good there. Now the second part says B, assuming the kinetic energy found in A is the maximum kinetic energy that it could have, calculate the work function of the metal. So basically, they want this right here to be the kinetic energy max. Well, I know one equation on the AP equation sheet that relates to this. It is Einstein's. K max, so kinetic energy max, is equal to HF minus the work function. So they tell us at the beginning of the prompt that a photon of wavelength 250 nanometers. So this is our HF. F is equal to 250 nanometers. No, F is our frequency. We have to rearrange this and plug our lambda in, so our wavelength. We know F is equal to C over lambda. So we can switch that out. We get K max. We'll be able to just substitute K max in later, and we get H over C times lambda minus our work function. So then we can solve for our work function because we know that lambda is equal to, as they said before, 250 nanometers. So we'll get 250 nanometers. We'll convert that to meters. There's 1 times 10 to the 9th nanometers in 1 meter. So we get 250 times 10 to the negative 9th meters. And then we can basically just plug this in. And to get the work function, we can do K max plus the work function is equal to H times the speed of light divided by the wavelength. And then now we subtract our K max from both sides, and we get H C over lambda minus our K kinetic energy max. And we found our kinetic energy max. An important part here is make sure when you're plugging this value into your calculator, you're not plugging this value in. You're basically plugging the value that your calculator says, so you don't get a rounding error. Because we actually have, the decimal place actually goes much farther out. It goes 3.33515974, and we want to keep that so we don't get intermediate rounding error. So we'll keep this value the same. I'll just, for simplicity, I'll plug this in as 3.335 joules, and then I'll get this value, Hc divided by lambda. So our Planck's constant is 6.626 times 10 to the negative 34. And then we'll multiply this by the speed of light, which we know is 3 times 10 to the 8th. And then we'll divide this by our wavelength, which is, as we found here, just right here, it's 250 times 10 to the negative 9. So we get, for this, we get, and there is one, I guess I forgot to add 3 times 10 to the negative 19th. So that is one thing I forgot to add. So this will just be 3 times 10 to the negative 19th. And then this value right here is approximately 7.9512 times 10 to the negative 19th. We'll subtract this to get the work function. And remember, to avoid intermediate rounding error, you just plug what your calculator has in. So we'll do the 3.33515974 times 10 to the negative 19th. And we'll subtract this from 7.9512 times 10 to the negative 19th. And we get our work function to be negative 4.16 times 10 to the negative 19th. Interesting. So we got negative value. That is interesting. I think I must have done something wrong then with my calculations. Okay, I know what I did wrong. I plugged in the value first. Okay, so basically I first did the 3.335, and then I subtracted that from 7.9512, which is where I went wrong. So I'll do second answer. I'll redo this and just subtract it from our 3.335 value. So minus 3.33515974 times 10 to the negative 19th. Okay, and then now I got instead 4.6160426 times 10 to the negative 19th joules. So that's our work function. So this is approximately 4.61. We'll just round it to two decimal places. We'll say 4.62 joules. 4.62 times 10 to the negative 19th joules. And often the work function will be expressed in electron volts. So most people will just convert this to electron volts. The AP sheet has a handy measurement value. It just says 1 electron volt is equal to 1.6 times 10 to the negative 19th joules, and that's 1 electron volt. So we can just divide it by our electron volt value of 1.6 times 10 to the negative 19th joules to cancel the units, and we get 2.89 electron volts. So that's kind of a nicer, we don't have that crazy times 10 to the negative 19th value. And then our last part of the problem said, the incident photon was created when an atom underwent an electronic transition. Okay, so it's basically saying we have this atom here. You could say that's a nucleus right there, and then this is like the orbit. You could maybe consider this a Bohr atom, and it could be like 1 electron is going from here to there, and as we know, there's a photon that would escape, because if it's losing energy, the energy is conserved, so some energy has to transfer out some other way. And so it says on the energy level diagram, on the atom below, the transition labeled X corresponds to a photon wavelength of 400 nanometers. Indicate which transition could be the source of the original 250 nanometer photon by circling the correct letter. So it's basically saying we have similar to this right here, our photon. With some wavelength here, we're getting this photon of 250 nanometers. And it's asking us, this says 400. This is actually 400 nanometers. So this is 400 nanometers, and it's asking us what transition would get us 250 nanometers. To solve this part of the problem, we have to go back to these two equations, E equals HF, and lambda is equal to C over F. So we can rearrange, and we get F is equal to C over lambda, and so our energy is equal to H times C over lambda. So that means that if the energy increases, our wavelength decreases. That's an important distinction to make here, because the bigger you go down, the more energy, the bigger the energy drop is. So if we want to get a wavelength that is smaller than 400 nanometers, we see that we need an energy jump that is bigger than this X value right here. So we actually are going to need something bigger, something like this. And D fits that perfectly. The reason we don't want E is because it's going the other way. It's going this way, and that means there would be a photon that the electron would need to absorb to get that energy increase. And so that is the answer to all three parts of this problem. Thank you for watching.